Hello, my name is Ahmed and welcome to my final year graduation project presentation. According to the Turkish Statistical Institute, over 88% of accidents were due to driver errors. This project aims to reduce such incidents by developing an AI-supported lane and traffic sign detection and recognition system. Deep learning was chosen as a core approach for this project because of its proven ability to automatically learn complex high-level representations from raw image data. However, the challenge lies in choosing the most suitable model architecture that strikes a balance between computational cost and recognition accuracy. The selection of an appropriate deep learning model is one of the most crucial steps in the development of the traffic recognition system. I tested and compared several algorithms like convolutional neural networks, CNNs, region-based convolutional networks, RCNNs, fast RCNNs, faster RCNNs, and YOLO. Unlike traditional object detection frameworks such as RCNN and its variants, which rely on two-stage processes, first generating region proposals and then running the classification and bounding box regression on each proposal, YOLO follows a single-stage architecture that directly detects objects in a single pass through the network. The core idea behind network is to treat object detection as a regression problem. This approach enables YOLO to process entire images during training and inference, which helps capture contextual information about objects and their relationships. One of YOLO's greatest strengths lies in its speed. Because detection is performed in a single neural network evaluation, YOLO can achieve real-time performance. YOLO model's performance heavily depends on the diversity, accuracy, and relevance of the training data. The focus is on collecting data that accurately represents real-world scenarios. I combined several images and videos from many different sources like open-source datasets, YouTube videos, and synthetic images, and I was able to collect and annotate 15,000 images of 46 different traffic signs. The training process focused on fine-tuning a YOLO model using my own dataset. I used Python, PyTorch, and Ultralytics, which provided a streamlined and flexible training environment. I utilized CUDA on an RTX GPU. This allowed me to train the model significantly faster than using a CPU, enabling experimentation with different hyperparameters and model sizes. The dataset was divided into 70% for training and 30% for validation and testing, and the model achieved a strong accuracy of 93%. The Raspberry Pi 5 was chosen as the main processing board for this project because of its powerful performance, compact size, and affordability. To ensure stable operation during intensive processing tasks, I integrated an active cooling system into the setup. To run the largest possible deep learning model while maintaining a smooth 30 frames per second, I added an AI hat with a 13 TOPS NPU accelerator for image capture. The system uses Raspberry Pi camera module 3. After the training process, the model is saved in a PyTorch file. However, the AI accelerator can't run PyTorch files directly, so the model needs to be converted into a compatible format like HEF. Since the Halo compiler doesn't support Windows, I automated the compilation process by creating and using Docker images. The compilation process came with several challenges. Due to the hardware limitations, I couldn't compile the largest and most accurate models, but the best model isn't always the one with the highest accuracy. It's the one that balances performance and feasibility. I approached this as an optimization problem. To find the most effective model my hardware could actually support, I tested different versions and sizes of YOLO, tweaking parameters, dataset sizes, and training settings to find the right balance between accuracy, speed, and compatibility with the AI accelerator. To develop the lane detection system, a pipeline was designed using Python and OpenCV to process video frames and detect lane boundaries. The lane detection process begins by reading the video frame by frame and resizing each frame. The region of interest is then masked and a perspective transformation is applied to generate a bird's eye view of the road. A binary threshold is applied to isolate lane markings, and a histogram is generated to identify the columns with the highest concentration of white pixels indicating potential lane lines. Using this data, contours are extracted and a sliding window technique is applied to track the lane markings across the frame. This approach allows for the detection of both straight and curved lanes by fitting a smooth line through the detected segments. Finally, the identified lanes are overlaid on the original frame using weighted image blending, resulting in a clear and visually integrated lane detection output. This is a video of me and Dr. Hakan testing the system using his car.